All right, folks, it's Bass Action back in action here. We're going to continue our discussion of finding composite functions, and we're going to extend it and actually also find the domain of some more complex composite functions. So, when we begin our discussion for the domain of a composite function, let's fill in a couple blanks here at the top. It says the domain of, if we wanted to fill these in, we would say the domain of f of g of x is a subset of the domain of g of x. Now we can translate this a little bit in that when we're talking about this f of g of x, that's just helping us describe a specific composite function. Okay, so that's all. They're just giving us a specific one to consider, a specific composite function there. And when they talk about g of x here, what they're wanting to call your attention to is to recognize that the domain is going to be a subset of what we called earlier the inner function. Okay, so if you've been in my class for a while, you'll also often hear me refer to some of these things as the peanut problem, and that we think of this inner function as like the ingredient. So in a recipe, and if we put some peanuts in there, we need to think about our ingredients always as carrying some type of a weight or a consideration in terms of allergens, or in our cases, our domain restrictions. So let's jump into our composite function here. You can notice this one's going to be a little more complicated than what we did before. And on this problem, I wrote this in the Goff notation. And as I mentioned before, I always like to rewrite this. So I'm going to rewrite this as g of f of x. I think that's useful. I also like to write the outer function. Remember, f of x would be our inner function. G would be our outer function. I like to write that outer function first. So I'm going to write g of x. Helps me better identify where I'm going to substitute. I'm going to grab that from the top of the page, and it's going to be 4 over x minus 1. So just a little review. Remember, if we were evaluating this for, let's say, g of 3, we would put that 3 everywhere that we saw an x. If there was x in multiple places, we would put the 3 everywhere. So when we, on our problem, are going to find g of f of x, so instead my inner is not just going to be a number, it's going to be my actual function f of x. That means that everywhere that I see x, I'm going to replace with the f of x function. So I'm going to color code this like I did on the previous page. So I'll have a 4. And where I had my x, I'm going to replace that with the f of x function, 1 over x plus 2. And I'm going to have my minus 1. If you've been in my class for a while, you'll recall that I always like to write these as an over 1. So I think of it as soon as I write something as a fraction, I write everything else as a fraction. Makes it a little bit easier to find my common denominators, keep things lined up. So I'm going to multiply my x plus 2 and my x plus 2 on the top and bottom to get my common denominator. And I'm also, again, if you've been in my class for a while, watching my videos, I always like to change that negative to a positive, and I like to write the negative up top. Just makes it a little bit easier to keep track when we distribute that negative in a little bit. So on our next step, we're going to keep our numerator as a 4. The denominator now, I'm going to actually have a rational expression here in the denominator. So I'm going to remember to distribute that negative when I write that 1. So I'm going to have my 1, and I'm going to have minus an x minus a 2. And that's all going to be over my common denominator of x plus 2. If this looks a little complicated to you, you can color code this and maybe just color that big fraction bar. Just a different color might make that a little easier to see. In the next step, we're going to switch from our fraction notation to multiplication, because what we're going to think is 4 divided by this expression here could also be thought of as 4 times the reciprocal of this. So when I go to write that one, I'm going to have 4, I'm going to put it over 1 so I can line up numerators, denominators, times my reciprocal, so I'll have my x plus 2, and then collecting my like terms here, I'll have my negative x minus 1. And I can pull this all together. I don't have to distribute or simplify if I don't want to. So I can leave this as 4 over x plus 2 over negative x minus 1. So when it asks you to find the composite function, this is your answer. So that is the composed function or the composite function. Now, when I want to find the domain, I've broken it down here in a couple ways. This one's actually pretty easy to do in our head, but we'll have some more complicated ones that these number lines will be useful. So the first thing that we're going to do is we are going to create a number line specifically to identify any restrictions for the composed function. Remember, the composed function is what we just found. So if I think of this in terms of a number line, when I look at this fraction, I have to think, hey, what is my denominator? When is the denominator going to become 0? And my denominator on this one is going to become 0 at a negative 1. So I can put that on my number line, recognizing that everything else is going to work just fine. Again, on this one, the number line's not really necessary, but as we get into some of our radicals, it'll become a little more useful to have the number line. The next thing that we're going to do is we're going to create another number line that would help us identify the domain restrictions for our inner function. In this case, remember, our inner function was f of x. So we're going to go back to our original problem, and we're going to look for any domain restrictions we would have on the f of x function. And of course, again, we have this fraction. The denominator here would become 0 at a negative 2, so I'm going to put that on my number line. Of course, everything else is going to work just fine. We've reviewed this idea quite often in the semester. So then when we combine our two domains, we can see that the only restrictions that we need to consider would be this single hole and this single hole right here, and those would be the only values that need to be excluded. So set notation is going to be our best option here. So we'll say x such that x is not equal to a negative 2 or a negative 1. And that would be our domain for our composed function. So really the big idea here is remembering this step right here, and that we always have to consider the inner function. Otherwise, we would lose this element right here. And that's all that we've got, and we'll work on a little bit more in class.